So this is my introduction for the interactive concepts, interactive advanced concepts, as well as the discussion. This is for, we're going back from week 3 to go ahead to discuss what I chose. Some of the questions I am going to be answering in this video are going to be what are the Lewis structures, if there's any good resonance, if there's any polar bonds in this, if there's any polarity of molecules, showing the electron geometry for inferior atoms, showing the molecular geometry for the covalent bonds portion of the molecules, demonstrating what they actually look like, and also answering what kind of bonds, if there's any, what kind of bonds will occur within the molecules between the atoms. Okay, so before I go into those questions, a little bit of a background of what chemical I chose. So I chose benzoyl peroxide, which is an acne wash. Typically, it's used for people who suffer from acne. You kind of put this on. It's supposed to help break down and everything and kind of diminish your acne. But specifically in this is going to be benzoic acid. So benzoic acid structure is going to be what, like, it is there's 7 carbons, sorry, there's 6 hydrogens and 2 oxygens, and it's a benzene based carboxylic acid that we found in like our that's found in a specific tree. We use this for, like I said, acne as well as some foods and beverages as well. But the way that it works is that it kind of cleaves or kind of like breaks apart into and I'm probably gonna pronounce this right, benzoic radicals through hydrolysis, and it creates that benzoic acid and benzyl radicals, creating that oxidization within our pores that can eliminate any acne causing bacteria or inflamed cells. That's pretty much a little bit about what it is before we actually go into like the breakdown of the questions I'm going to be asking. All right, so first is going to be the Lewis structure of the benzoic acid. I kind of broke it down into 2 ways. One as if it was like a ring with all the double bonds on it, the other one without the rings. And then we have our kind of double bonds here. I tried to make it so it gave a lot of options. So this is going to be, oh, sorry. This is going to be the Lewis structure of what benzoic acid is in 2 different forms. Okay, so in the second question is asking, are there any good resonance for benzoic acid? And there are. I'm going to put it down for a bit. This is going to be, there are 5 of them. I wrote the original one over here, and then we're just kind of going over here. So the first one, which kind of looks like a backwards 7, this is where we see that within that, the double bond between like the C and the O, that carbolic group kind of will break. That's when the oxygen gets a lot more negative, as you can see over here, and then the carbon gets like a positive charge. Then it creates like a new pi bond between like the second and the second carbon and the functional group. Moving on to the second one, this is where we see like there's the pi bond between like the 5th and the 6th carbon will then break and create a new pi bond between like the first and the, so pretty much it just seems like we're just almost kind of like in a weird way playing like proper musical chairs, because you see in the third structure over here, this is where the pi bond will break between the 3rd and the 4th, creating this new pi bond between the 4th and the 5th, and then the 4th one is doing the same thing where this is where the pi bond will break between the 2nd and the 3rd function, creating a new pi bond between the 2nd and 3rd, and then lastly the 5th one, this is where we see that the pi bond kind of the pi bond will form between the carbon and the oxygen in the functional group. So it just feels like we're kind of playing, like moving all over, playing a weird version of musical chairs. All right, so to kind of answer question 3 and 4, if there's any individual polar bonds within the molecules, yes. And if there's any polarities of the molecule or like duo dipoles, I decided to put back on the charts. So as we can see, the C to H is highly polar. Then we have the O, the oxygen to the carbon to the hydrogen, highly polar. Oxygen to the carbon, kind of polar bonds, as well as the oxygen to the hydrogen, polar bond. And for the dipoles, Down here are going to be the carbon, that's a double bond to the oxygen, and then the hydrogen, the oxygen with the hydrogen. All right, so this is the structure that I have for my benzoic acid. I don't know if it's cheating because I've had these laying around for many, many years, but we're just gonna go with this. So as you see, if I pop this up, we just have the ring of the benzoic acid. So everything that is in black represents the carbon, everything in white represents the hydrogen. And when I attach this, it has my structure. And the red are going to be the oxygen. So this is how my structure looks. Now, as far as like the covalent, so it's saying for number 6, we're showing the electron geometry as well as the molecular geometry for the covalent portion of the molecule. So for that, it looks like there's two portions that are consistent of being covalent. One is which is the benzoic ring, and with the ring, it looks like it's showing a shape of the triclinolar plantar because of the fact of like, see it goes over here, boom, boom, kind of like this. But then there's also a that carboxyl group, which I believe is this, and it is also showing when I detach it. It's also showing that transgenal. I'm probably pronouncing it wrong. Transgenal plantar segment of it. So pretty much, yeah, they're both like the angle of it is ranging between like 120 for this bond. So that is pretty much it. It has, I believe it has, it has 4 lone pairs, 19 bonds as well. And so this is kind of the shape that I kind of built for my benzoic acid. So as well as this one also has sp2 and sp3 hybridization for this bond. Okay, and lastly, to answer one of the questions about the different types of bondings within the molecule and between. So, down a little bit. Okay, so within the bonding, we have some covalent bonds. And specifically, the covalent bonds are going to be where the benzoic rings are going to be, as well as the carboxyl group. And these bonds, when they're formed, they kind of share electrons, as well as are in between the molecules. So we have a couple different ones. Let me put this, okay. So we have our hydrogen bonding groups, and that is going to be like our OH and our CO. And for the hydrogen groups, they bond together with the hydrogens of the hydroxyl group. And the carboxyl group as well. And the hydrogen bond, and this is going to be special because it has a dipole-dipole like interaction that is highly electronegative, high electronegativity with like the atoms as well. Another one that we have, I don't know if we talked about this, but Van der Waals force, I found this all online. This also has, because it has a London dispersion force and a dipole-dipole interaction. And these forces, I guess they arise temporarily in the electron distribution. And lastly is going to be the pi-bi interaction, which happens in the benzoic ring. There's this pi to pi interaction that has this adjacent to the aromatic ring, and these contribute to the overall stability of the molecule.